informative, lots of materials. So I think it's very nice. Yeah, I learned a lot from this webinar because I'm not expert in space weather. So going through the YouTube video, recorded video, it helped me a lot to learn.
Yeah. It's very good to hear that, Dr. Manata. This is a lot of effort that we put into this to bring it to our people, particularly from the African country around the region of interest. We want to educate people as much as possible about the instrument so that at the time we get funding to put the instrument at the locations, we already have people at hand that can actually use the instrument, can help with it, maintain the instrument and all of the necessary things that we need people to do. So hearing this from you, it's very encouraging, and I thank you for that. And also, I think I'm going to get started by sharing my screen.
Okay, good afternoon.
Yes, sir. Good afternoon. Dr. Joseph, how are you, sir?
I'm fine. I'm excited to be part of today's program of CONGA. I think this should be my first or second time of attending the meeting, mostly online.
Okay.
My name is Dr. Dodo Joseph from Nigeria. I'm a research director with the Nigerian Space Agency. In a couple of years back, I have been the center director at the Center for Geodesy and Geodynamics. The center is located in Toro Bauchi State, more or less like central Nigeria. My background is geodesy. I'm a space geodesy inclined. So I've been doing a couple of work. We've done a couple of work in the area of using GNSS. GNSS is my major area of specialty, using GNSS for basically geodetic activities and as well as being part of space weather and particularly the troposphere. My PhD work was basically on troposphere, using the GPS data to model tropospheric delay and coming out with different algorithms. So I've been working with GNSS since 2004, where I started from University of Nottingham in the UK. And then thereafter, I was at the University of Technology Malaysia, where I backed my PhD in 2009. And I've also been participating in lecturing. I'm an associate professor of space geodesy. I've graduated a couple of students, even in the field of using GNSS for ionospheric studies, as well as using GNSS for tropospheric studies. So I'm so excited to be part of this group and also to particularly attend today's presentation. Thank you so much for the opportunity.
Yes, thank you very much, Dr. Dudu. We are very grateful that you are here this morning to participate in this program, and we thank you for coming and helping the students and graduating those students in different fields. And thank you for that detailed introduction of yourself. And at the time that we need you, we already know you, given that you introduced yourself today. So we encourage people to introduce themselves as much as they can. It's really good for us. And also, Dr. Joseph, if you, in the future, since you have a different aspect of view with using GNSS receivers or sensors, we can also invite you to give your perspective on the area you are interested in. All of these things are very helpful. So we look forward to, if you want to give any presentation, you can go to our website. We have the website where you can actually enrolled to do that. So, but for this year, I think we are already there is no more space for presentation. We have people that will present for the rest of the year. So maybe next year will be a good time if you are interested in doing that.
Okay, thank you so much. It's my pleasure to be on this platform. Thank you.
Yeah, and I will share my screen now. I think I shared it before, or the point again. So let me try to do that again, and then we will get started. So it's coming up. I see some familiar faces. I see Dr. Yinka. I see Dr. Ivan. Like he's here. I haven't seen Jorginho. I see John Bosco, my good friend. So thank you all for making it to the program today. And everybody as well. So don't say, oh, Jonah did not mention me. Yeah, so I'm trying to share my screen. It's coming up. And there you go. Please. Yeah. Can you see my screen? It's a little bit slow. I don't know why.
Yes, we can.
Okay, so let me make it bigger. Is it okay? Can you see it, the full screen?
Yes, we can.
Okay, thank you very much.
Yeah, it's okay.
Okay, thank you. So today we are getting started. It's 26th edition of CONGA meeting series. And our guest speaker today is the associate professor from the University of Tokyo. And we have had him in the past. I mentioned that earlier. And he presented a lot of detail about low-cost receivers in our last meeting. He actually demonstrated how they work, and it was a very nice webinar. But we didn't have much time to complete all of the detail, and I said, oh, we need more time. So today, I have him again, the privilege to have Dr. Manadhar with us again. I'm going to give more detail about his introduction. I have his bio, which I'm going to read to us at some point before he now presents his presentation today. But before we get to that, we know that CONGA is a meeting where we can all contribute. So feel free to contribute your whatever you want to contribute to this program, maybe your opinion or your area of expertise or what you think it should be, and all of those things. Everybody is welcome. And then we know that we usually have introduction at the beginning where people introduce themselves. We are privileged to have Dr. Dudu today to introduce himself. And if you want to introduce yourself, always feel free to do so. And today we also have people from LDI and University of Space Science Lab at the University of Lowell joining us, and they are parcel of this program, and we are working on together to make a prototype design for CONGA. So it is a privilege to have them in the meeting today, and they will always join this meeting from now on. So, but this is a special one because they wanted to see how Dr. Manadhar has been working on low-cost receivers. As we know, I have this image on the left to show us that the importance of CONGA. We are interested in this area of this equatorial region area where there is a hole over the African sector. And there are, as you know, there are a lot of dynamics, electrodynamics, plasma dynamics that are going on in that area where scientists are very interested in studying, survey, geodesy, and all of the areas. They are interested in this region. And we are working together to bring multiple instruments around this region, not only GNSS receiver, because when we are able to do this, we are able to do these GNSS sensors over this region. As you can see, these are locations around the equatorial and low latitude region. We will be able to co-locate other instruments like magnetometer and all other small scale instrument that we can co-locate in the same region. So this is the beginning of a very big thing, you know. So I'm very excited for this program. And if I move to the next slide, I just try to explain a little bit of the goal of this meeting, because this part of the program is to build a collaborative effort and data-ready database for the community. You know, when we build a collaborative effort, starting from this kind of meeting, we get to know ourselves. It becomes very important aspect of the project. So we create a network of people that can work together. We train and develop members to understand and to be able to use the grant-based instruments, especially students. We help lecturers, they bring their students over here. Some of them, they give presentation in the past. We have had students come to this to give presentation on their thesis or dissertation. So this is very helpful program. And we also want to encourage, in this program, we encourage people to freely give their data to the community. The research community, the scientific community needs data to actually bring the best of the results, you know, to be able to showcase what is going on. Some people tell me, we have data in Africa, but it's not released. So we want people to try to, as much as possible, to make their data available for the scientific community in particular. Let me see. I think I'm having some interference. I'm going to mute this person. Okay, so that is that. And today, we're getting started. Today, we have the privilege, like I said, to have Dr. Manadhar again with us. Dr. Manadhar works for the University of Tokyo as an associate professor until March 2025. He is one of the founder of Location Mind Intercorporation, Japan, which was established in February 2019. I think that is a AI project sensor location that they are doing, and I have heard about that company. And he joined this company as a chief development officer in April 2025. He has also been an employee of the Japan Aerospace Exploration Agency since May 2026. In addition, he is affiliated to the University of Tokyo and Tokyo University of Marine Science and Technology as a visiting researcher. Professor Manadhar has extensive experience in GNSS signal design, signal analysis, and signal analysis. He developed a GNSS signal authentication system for quasi-zenith satellite system, Japan's region satellite navigation system, to authenticate GNSS, Galileo, and the quasi-zenith satellite system signals and detect smoothing attacks. So as you can see, Professor Manadhar has been into the hardware part, mostly the hardware part of the GNSS sensors or receivers. And I have seen most of his webinar online. And today we have the privilege to welcome Dr. Manadhar to our platform. And we give him floor to start his presentation while I stop sharing my screen. So, Professor Manadhar, the floor is yours. We have
thank
30
you.
to 45 minutes thereabouts, and then there will be questions and discussions after that. Thank you.
Okay. Okay. Yeah. Thank you very much for the introduction. So within this 1 year, so there are a lot of changes for me, including my affiliations from university, private companies, again, universities. So maybe you are a little bit confused with my affiliations, associate professor or research, so many things. But anyway, so I have a slide let me share my slide. Okay. Let me share. Mhm. Okay. Can you see my slide in the
Yes,
presentation mode? Okay.
very good.
Okay. So, okay. So I put my title, Findings of Low Cost GNSS Receiver System for TEC Computation. I think the first presentation I had was, I think, about 2 years ago on whether low-cost receivers are good enough for space weather like TEC. And after that, then I explained about the low-cost receivers, how to collect the data using N-trip and some other, the data collection, raw data types, and so on. And I think this is my third one. And now, within these 2 years, we have some results. I mean, the results to verify that it is possible to use the low-cost receiver for TEC. So this is my presentation today. But as you know, that I'm not expert on the space weather, but I work more on the signal analysis, signal design, and also the hardware, the little bit of system integration for the low-cost receiver system for high accuracy signal authentication or interference jamming analysis and so on. And when we do this, so then I thought that it would also be useful for the space weather, and this is how I got connected to this community of the space weather experts. So I'm very happy to learn from you with so many webinars so far for the last two years or more. And yeah, today I'm presenting as from the University of Tokyo, but actually, so now my main affiliation is a private company called Location Mind, which we established a few years back, 6 years back. And now I'm working as a Chief Development Officer or CDO. And also I'm working as a senior engineer at the JAXA, which is the space agency in Japan, only from this year, few months back. And then once I joined the private company, so I left the University of Tokyo, where I served as an associate professor until March 2025. And after I left the university, I didn't leave, but I still as a visiting researcher. So my affiliation is now visiting researcher at the University of Tokyo, and you can use our resources or we can provide the data and all. So we still have everything there. So we can use the facilities at the University of Tokyo for the research purpose, the data sharing and all. And also we have now new project to develop new things in the GNSS under the government project called the JAXA SX Crane project, which is very large. And under this, we are going to develop new things, many new things in related to GNSS. And this is how I also got connected to Tokyo University of Marine Science and Technology, where a lot of GNSS related research are conducted. Unfortunately, they also don't do space weather. Okay, so it's very few. I mean, in my network here, there are people in Japan who does a lot of space weather, but they are from different community, another community, not in my network. But we are connected somehow. So this is my background and what I do. And if you want to do more on the signal processing, signal analysis, and also if you want to get the data from me, so let me know. So this I've been requesting, I've been informing you all the time. So also, probably I would also like to use your data if possible. Okay, because data from Africa and the satellites that's visible at your site and our site is probably completely different. I mean, signal is same, but there may be some completely different impact of this weather. And part, one thing very important for this type of data sharing is to log the data at the same time to see how it looks like. Okay? This is one of the things I am interested. Okay, so let me start with this brief background information. Oh. So this is a low-cost, high-accuracy receiver system for space weather, and we evaluated. Actually, we thought we could evaluate more, but somehow, due to many constraints like the time and resources, not I mean, the human resource or the time. So we were able to do detailed analysis on two receivers, F9P and Mosaic. So these are the two things on the low cost. And at the high end, we use the Trimble Neta 9 and Septentrio Polaris 5. So we have the data from four different receivers, two low cost, two high end receivers. Okay. And here are the F9P, which I suppose many of you are also using. And you know, F9P is available in two different versions, L1, L2 or L1, L5. Okay? You don't find L1, L2, L5 in the same receiver. So u-blox has a new receiver. I should have put here the X20 that's newly released. I have a few sets with me, but I didn't have time to analyze the data from X20. But for me, F9P is very useful. And I like this F9P receiver because I work a lot on that. I know how it looks like, and if there's a problem, debugging is much easier for me. And the another good receiver is Septentrio Mosaic, which is all GNSS signal and it's all frequency, means L1, L2, L5. And also you can have L6, okay? If you choose L6, then you will be L1, L2, L6, not L1, L5, L6. So if you have L6, you can also receive the Galileo E6 signal. It's the same frequency. So we use L6 for high accuracy in Japan. So that's why I use the L1, L2, L6 combination. Okay. And then these receivers, both F9P and Mosaic, provides raw data necessary for high accuracy space weather or signal authentication and so on. And for high accuracy, you need the port phase, carrier phase data, Doppler information, and so on. And this is same for the space weather as well. So if you have a carrier phase data, port phase, carrier phase data, so this will help you to compute the space weather related information. Okay. And of course, you need at least two frequency, L1, L2 or L1, L5. But so far, I found that many software which you have developed, I think they are more towards L1, L2 signal processing, not L1, L5. But many people, many researchers, they have also now modified their software to process L1, L5 as well. And then this navigation frame data is not necessary it's not necessary for space weather. You just need the raw data, like Rhinex data, which we call the raw data. And this navigation frame data is the data bits itself, which is necessary for signal authentication to detect the spoofing attacks. So, but you don't need it for the space weather. Also, this is necessary for the early warning system. So this is a service that is provided by the Japanese satellite. Okay. So yesterday we had a huge earthquake in the southern part of Japan, 7.2 Richter scale, and many buildings were damaged and several people injured as well. And during those type of disaster, so we can use this GNSS signal to provide early warning messages, okay, or post warning messages. So that's one example of how you can use the GNSS signal during the natural disasters, okay, or any type of disaster, natural or man-made. Okay. And these receivers are quite good. So F9P can provide output up to 20 hertz, and that's the maximum. But the Mosaic can provide up to 100 hertz, only the measurement data. So this raw data, it can provide at 100. But the position data is up to 50 hertz only. Okay. It cannot provide 100 hertz position data output. And they can provide both of them RTK and PPP capable for high accuracy. And oh, this I need to update. This is the old slide. Sorry, TEC Computation. It was my previous slide 2 years back to be explored. Now we already explore, and we found that it can be done. Okay. Now the other thing is for computation. So this is another issue. We looked at whether we can really compute the S4, the scintillation. Okay. The code phase scintillation, whether we can do this. And this is quite challenging. So normally to compute the scintillation data, you need the raw data, the power output at a very high rate, 100 hertz or like that. And also you need actually the IQ data itself if you can get, but the receivers don't provide, not IQ data, sorry, the tracking output. Okay? But the receivers don't provide such type of output because it's too much memory and too much processing load for the receiver to output such data. But there are researchers who actually tried the S4 computation with 20 hertz or 50 hertz output. And I will show you this output, how it looks like. It's not my work. It's done by the Boston College. So they presented us how it looks like and what are the difficulties. So I have some results. I mean, something to show you. It's not my work, but someone else. But they also presented to me for our working group on the space weather. We have another working group working on that. So there are some things we have, and also we need to explore this. And to enable this type of computation using the low cost. So normally it's not possible to do that, but the code phase S4 to some extent, if you have a good receiver like F9P or I also maybe the Mosaic, I think they can output, but it's a bit tricky. So we need to see the results, how it looks like. Okay. And the cost of F9P is about $300 to 300, but the Mosaic is a bit expensive. Now they have released the cheaper one, Mosaic Go 5, I think. That's cheaper, and that's about $300 as well. The standard Mosaic is about $500 or $600. Yeah. But I think that even the cheaper one, that's also capable of providing you this TC data. And this is how it looks like, the one we have. So this one, so we use F9P for many different types of applications for the high accuracy. And this is a Madoka PPP receiver, and this same receiver can also be used for the space weather. And this is some prototype developed by one of our team members by using the different types of modules here. So some customized board to make the low cost system, which can also be used for high accuracy space weather and other things, other applications like authentication and so on. And this is the one example of the Mosaic receiver type. So I like the Mosaic very much because it's quite compact and I can have three frequencies, L1, L2, L5 or L1, L2, L6. Also, it has, depending on what type of Mosaic you purchase, so it also has a Ethernet interface, so you can connect directly to your internet. And it also has a processor inside, so you don't need a computer. That's a very big thing for us. So if you use F9P, you still need a processor. You need a computer to connect it. But Mosaic, you don't need it. Okay? You just connect, and then it can save the data internally in the SD card, or you can send the data through the entry or through the Ethernet to the remote server. I mean, remote location. Okay? So that's a good part for the Mosaic. But you need to know which version of Mosaic. There are different types of Mosaic versions which can do this or which cannot do that. I think most of the Mosaic they can do without, they can run without the computer. You just need to set once and that's all. So this is very useful. So but the cost is a little bit higher. But even if the cost is higher, so if you don't need the computer, so you don't need the other things, so you just connect the antenna and then you get the output, everything. And this is how we log the data. Now I will explain how we log the data for this TEC computation. You see, we have an antenna on the rooftop, and we have a splitter, signal splitter. I think actually this is 8-port splitter. I didn't show all. So I just showed the 4 ports here, and they are connected like this. So we have a Trimble receiver as a reference, the NetR9. We have a Septentrio Polar RS5 as a reference. These are two high-end receivers. Maybe it's costing Trimble, I think it's the one we have is I think $10,000 or more. This is also almost a similar price. And then we have a Septentrio Mosaic and u-blox F9P as a low-cost receiver, dual frequency or triple frequency. Low-cost receivers here too. And it's connected to the same antenna. Okay, so same antenna, but a different receiver. And then we log the data through the encrypt server to a hard disk. And then we use this data to compute the TEC or ROTI. Yeah. So this is what we did. And now we have data logged by 4 different types of receivers using the same antenna. And also you have an option of processing data using different types of software. So you can get this data and use your own software to see how the results look like. This is what we want to do. So now I think few people, they use this data and they computed the TEC ROTI and see whether the TEC from the Trimble, Septentrio, and Mosaic F9P are similar or not, okay? Because it's the same antenna data. So your output, although the receivers are different, they should be very much similar. So this is what we like to see. And also, depending on how you process, the results may differ. I mean, your algorithm to process the TC data or ROTI, basically it's same, but depending on some setting of the parameter or how you select the satellites, what is the mask angle you put, so they may have some impact on the output. And these data were logged in, it's not in Tokyo, but about 30 kilometer north of Tokyo. So these are the coordinates. Yeah. And to process this, we use the software from the KMITL, King Mongkut Institute of Technology in Thailand, and also the Bruno from ICTP. So he helped me to process the data. And these are the data set that we logged from different receiver, NETA9, Polaris 5, Mosaic, and u-blox 95, and GPS, GLONASS, Galileo, QZ, SBAR. So all this data we have, but we use only GPS. Okay. And these are the results, right? So if you look here, don't look at this black line for the time being. So this is a liquid output. So if you forget this black line, and then you see very nice overlay between the net R9. So this is red one is F9P, MS is Mosaic, R9 is the Trimble net R9, and X5 is the Polar X5 Septentrio. Okay. And when you overlay these four receiver data, you see very nice match, very nice overlay. We don't see significant difference between the values computed by low-cost receiver and the high-end receivers. So these are our conclusions that we can use the low-cost receivers like F9P or the Mosaic to compute the TEC and other TEC related parameters. Okay, and he also used a NICIC model to compute the TEC, and from that he overlaid the data. Okay, there's some difference here between NICIC and the ones we got. So we don't know how good or how bad is this thing, but for me, the trend, the trend of this curve follows the actual our computational TC. The trend is okay, but the values are different. Okay, so I think it's okay, but maybe there's something difference between the NICIC model and the actual the TC computed from the data. Okay. So these are the some things that probably we need to look at when you look like a NICIC and our this computation. Why is such a difference? But all the computation from other receivers, they overlay each other without measure deviation or difference. And based on these results, so I think we also published a paper in this book. It's published, so you can search with this name and title, our name, Bruno, Dinesh, and so on. So Bruno is the lead author, and he published a paper here, so you can download this paper for a little bit of more information. And while we were doing this type of computation, and we found that some of the software, like we have this result is the result computed by the ICTP using the software from the ICTP. Also, we have a result similar to this computed by the Thailand KMITL. And when we look at this KMITL or some other software, so we found some bugs as well because sometimes the results are quite different for some data. So those type of bugs we solved actually. So my recommendation is that you better check your software, the processing software, make sure it's okay. Because if you don't look like at these sections of data very closely by dividing into maybe several minutes of data, then you will see probably something not correct. Okay, and this may happen because for the high-end receivers, the L2, because we use the L1 and L2, and normally in the low cost, we don't have L2 actually. The L2 is only the L1 the P we have, but L2 P we don't have it. Okay, there is because there's no civilian signal in L2. There's only the PY, which is a military signal for a military purpose. So the low cost receivers, they don't have this L2P signal. Okay? So, and if you don't have L2C output, so you can't use the L1 and L2 combination. So depending on your receiver, so there may be some limitations for the low cost. Okay? So make sure that you get necessary frequencies, data from the necessary frequencies and the low cost system. But anyway, as long as you use F9P and Mosaic, low cost Mosaic, so the results are, I think, quite satisfactory. I think. Okay. So we don't see much significant difference, and these data are for 3 continuous days. Okay. And if I go to so this was the previous slide. That was our main result, and then we had this discussion. Now that was the data only from one antenna. So then many people request what will happen if the antennas are changed. Okay. So if you change antenna type 2, 3, or 4, do you still get the same result? And if you change different types of receiver, how it will looks like, okay? Or if you change from L1, L2 to L1, L5, how this will look like. There are so many discussions after we showed this to people. They have so many questions, but to answer those is very difficult as well, because you really need to log the data like this. So maybe I need to have a one type of antenna for 7 days, log the data, and then replace by another antenna, or I should have different types of antenna at the same time as well. So you really need to set up the antenna, several antennas, and several sets of receivers, and then log the data simultaneously. That will be the best example if possible. It is possible in my case, provided somebody is interested to process the data. But I found very difficult somebody to volunteer to process the data. So if some of you are really ready to process the data, I will log the data as you need it, okay? Because we have the resources to log the data the way you want. We have many types of antenna. We can put maybe different types of the connections here, different types of receivers. And even now we have more different types of low-cost receiver from Sony, from Furuno, and maybe other makers from China that's also providing the high accuracy services. I think all those receivers should be tested if possible. So we don't have a problem of the hardware, the receivers, and this type of physical, I mean, the hardware devices we have. The problem is who will help to process the data. Okay? And also, data is one thing that we need. And then also we need different types of software actually, because many researchers have developed the software and they must be validated as well, whether your software is really working correctly or not. How to validate, how to make sure that the TC computed by you is correct. Okay? Because once you compute, you always see the graph as I showed before. But how to know that these TC values are correct? You do need some reference, but normally it's very difficult to have a reference. So I think we should, one recommendation from me is to log the data at the same time, but different places. Like this we did once in Bangkok and Tokyo, because they said that there was a problem with the low cost receiver. The data that there's some carrier the phase slip carrier slip, and then the data just jump. It doesn't look nice. But it was some other problem, not because of the low cost receiver. Okay? It was probably, I think, the bug in the software probably. So these type of things we discover when we were doing the logging the data simultaneously. Because when I log with the same receiver in Tokyo, there's no problem. But when they log the data with the same receiver in Bangkok, they had a problem. And I don't think that's due to the TEC, those type of problems. So we tried to find out, and after several months, they found that, oh, this is something else. It's not the TEC itself, but some other problems in the software or in the data processing method. This is how we solve. So my recommendation is that we should have some sort of a 3 or 4 days of the challenge. Uh, People in Europe, people in Africa, people in Asia, and different countries. So we should devote like this webinar, 1 hour, not just 1 hour, maybe several hours for a few days. And we say, okay, I will start logging the data in Tokyo. Now you log the data in Africa, different cities. There are so many people now. So we log the data, if possible, maybe 2 to 3 days. Okay, you can, if possible, you should run the receiver for 2 to 3 days. I prefer 1 week, but I think 1 week may be quite difficult. But at least 24 hours or 3 days minimum, that will be very nice. 3 days data. So it's different location logging simultaneously, and then those data we collect and we process with the different data with the same software, and then different software, and then evaluate them, yeah, whether we get the same curve or not. So I think these type of things must be done in the CONGA in your community as well. So this part is still I could not do it, although I've been talking this for last more than a year. We have data, but it was very difficult. And also I have a very special data from the aircraft. Okay? So we log the data from the aircraft, which is flying 800 kilometers per hour. But the point is whether the question is whether you can compute the ionospheric effects. I mean, whether you can compute the TC from such a data which is moving. So far, you are computing TC from a static antenna, okay? And you are looking the results for 1 hour average or several minutes of average data, not the 1 hour, sorry. So several minutes of data which you average aggregate. But if it's moving, so you have just one epoch of data, and it's continuously moving, and that also at a very, very high speed. So this is one challenging part. Maybe we can't do that, but it's just interest whether it's possible. So yeah, this is the summary. So to summarize, so I think we can use a low cost, and this is done by not only us, maybe many of you also did the same thing, and many other researchers also have very nice results as well. So I think we can say if we use a good low cost receiver, TC, ROTI computations are no problem. But we need to develop a software which can be used easily, and that can be integrated with the system, so that even a person who doesn't know what is GPS can log the data and output the curve, output the computation values. So this type of things must be done as well. And one thing is also necessary is data formats and processing algorithms shall be standardized for uniform results. So this is very, very challenging. So this is another problem. Okay? Which version of data we should use? Shall we use the Rhinex 2? It's too old. It doesn't comply with the new signals, so we must go to at least Rhinex 3 something, 3 dot something, the new version of Rhinex, and many algorithms. So they are developed for the older version of Rhinex. So if you don't upgrade to the new version, and you cannot use the new signals, new satellites, and so on. So they have to be updated for the new version of Rhinex. This is also one thing we found, like in the program by Flurry, which was designed to work with the Rhinex version 2, 2.2 point, yeah, that version. So it doesn't work with the new version. So you need to modify the data reading, uh, the programs, functions. And also we need to have a manual how to set up the receiver for the low cost. There must be some guideline. And one thing which I found in the low cost receiver, I didn't mention here, but the mass angle is bit critical. So if you go very low mass angle, like below 20 degrees, maybe your TEC computation is not so good. Okay. So my recommendation is that you make the mass angle a little bit high, 20 degrees, and then you get a quite comparable TC with respect to the high-end receivers. But for the high-end, it gives you a quite good result, even with a low mass angle of 10 degrees. Okay. But if you also set 10 degrees of low mass angle to the low-cost receiver, the TC is a bit noisy. It's not as good as when the mass angle is higher. And then we need to tell this type of output to the receiver manufacturers so that they may get encouraged to help us to output to modify the firmware even for S4 code phase. Carrier phase S4 FIFO is not possible. Right? Yeah, high output data. And then I also found when I did all this, so I found that there's a gap. I mean, there's a gap between the GNSS community and the space weather community, because the experts from the space weather, they know more about the physics. They are more the scientific experiments. They are expert on that, processing the data from the physics viewpoint or space weather, the science viewpoint. But the GNSS community, we know from the signal aspect how to process the GNSS signal, the digital signal processing, how to compute the position data. And when we look at the from the space weather viewpoint, so we don't know much. So there's I think very big gap here. So I think there must also be a very close collaboration between the GNSS community and the space weather community to bring this gap small, so that we can share the knowledge, information related with the receivers and so on. For example, for the space weather community, you are expert on processing the data, Rhinex data, if I provide, but you don't know much about the hardware, the antenna, the receivers, low cost. So what is the those the signal types L1, L2, L5, P code, Y code, M code, CA, and so on. And new signals are coming up, and new satellites are being launched. And there are so many satellites, so many signals. And if you want to use all those, so how will this affect the space weather competitions? So they are very, very important. But I really don't know to what extent this can be done. But I think there must be a closer relation between the two communities. Okay? There must be a bridge to connect these two communities. And I have some reference slides to show you for the S4. So this is the work done by the Boston College. So TL Beach. So if you want to know more about this, so please contact him. because he presented quite interesting results. So I don't put here, I just put the reference to contact him. And it was very convincing that even the low cost receiver can be used for S4, but some limitations, okay? And he has mentioned some of those things. There are some limitations, but you can get, yeah, some useful values, I think, depending on the case. So please discuss with him for more information. And these are some other outputs which we use to compute different types of the TEC values using the Polaris 5, some details. So uh, for the different, I think this is for different dates. Yeah, Polaris 5 and the Mosaic and F9P. Yeah, this is for 168, 169, 170, and 167, 168, 169, different days. Okay. Same receiver, different days, and how it looks like, and the Mosaic and the F9P. And there are some the data so impact of phase jump on TC computation. So like Bruno, who processed this data, he then prepared this graph, and he said that there is some phase jump in the TC computation with the low cost receiver. Okay? So this is one thing which he found it. Okay? So Polaris 5 versus Mosaic, because it's made by Septentrio both, so you don't see much. It's a Septentrio product, both high end and the low cost. But if you compare the Polaris 5 versus the u-blox, then you will see the jumps a little bit higher. Okay? But I don't think these are major issues to have all these the overall TEC competitions. Okay, so this is all from me. So thank you very much. And probably you have several comments or questions. So please ask me if you have anything.
Yes, thank you very, very much. Let's appreciate Dr. Manata for this wonderful presentation again. And I want to thank you particularly for your time. You know, right now it should be closing to 1 a.m. in Japan, and we have you.
It's 12:30, yes.
Yes, so I appreciate that a lot. You know, it's not easy to stay up at this late time of the hour in Japan. So I really appreciate you for that, for taking your time to educate us on more on this hardware aspect of the GNSS receiver. And having said that, I want to open the floor for questions. I know there are some questions in the chat. Let me see. If you can just um, ask your question. I think a couple of people have questions for you, Professor Manata. Bruno, you can
Okay.
go ahead with your question if you can.
Thank you very much, Dr. Jonah, and thank you, Professor, for the presentation. I just have two questions. One is on how can one monitor the antenna gain power for a particular antenna during the operation, just to be sure that the antenna is okay, it is in good shape. So the rest of the different variations in whatever we are analyzing, it's basically from the ionosphere itself. Then the second question is that I have seen online where people are trying to sell low-cost signal splitters. So my question is that during such tests, should we be so concerned about the quality of the signal splitter, or regardless of the price, the cost, and the number of ports a signal splitter has, it will not have any impact on the signal that is being split among the various receivers. Thank you very much.
Okay, so let me explain your first question about the antenna gain or the quality of the signal. So normally, I think, yeah, you should have a good antenna, but it doesn't mean that it should be very expensive. Okay. So nowadays we can find maybe 100, $200 good antennas well online. And I found, so you should buy an antenna that is certified for RTK. Okay. And you can buy maybe around $150, I think, nowadays, right? Well, that's quite good as well. So the antenna that we have here is not a very high end. This is just a few $100 antenna. I think it's less than $1,000. Okay? It's not a talking very huge big antenna. And to see whether your antenna is working well or not, so the only thing in the receiver you can check is the CN0, the signal level. If the satellite is 70 degree or above, your CN0 for L1, GPS L1 CA should be above 42 or more. Okay, so this is one indication. So if your CN0 is 42 or more, it's okay for the high elevation satellite. But even if your satellite is very high elevation, and your CN0 is uh, below 42, I think it's bad. Yeah. So normally, when the satellite is very high elevation, your CN0 will go up to 48 or 46, and 38 is the minimum to have a good measurement. Okay? So within these values, you should check it, especially the high elevation satellite. That's the easiest way, the manual way to see. There are other things to measure. Actually, some receivers also help you to see the AGC value itself, like the in the u-blox. So if you know how to check, so you can see, but it doesn't tell you exactly whether it's good or not. Okay? Septentrio also has this type of some sort of quality indicator of the signal. Okay? So software, the manufacturer software, they have something to tell you good or bad signal quality. But the best thing is just check the highest elevation satellite, GPS L1, CA, and see the CN0. So if the highest 70 degree or more, I think your CN0 at least 42, and normally it will be about 45 dB hertz. Okay? And the second question you asked is the low cost splitter, whether it's good. So I don't know which brand you are talking about. Okay. So the one I have one, this is called in stock wireless components. So this is, I'm using this, and this is a 4-port or 8-port or 2-port. And this is actually not low cost, but it's much cheaper than the special, the, okay, can you see this? So this is the one I'm using. Okay.
Oh, yes, 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 I can see it. Thank you.
Okay. So this is the one I'm using, and this is a 4-port. So you can buy this 2-port or 8-port, but once you add a splitter, it will have a loss of signal. So 4-port loss will be at least 2 dB or more. So if you put 2 to 3 dB, okay, 2 to 3 dB loss, this one, but also when you put 8-port, your loss will be about, it won't be 4 dB, but it will be at least 3 dB or more. Okay. So 3 to 4 dB loss, you will have it. So, and then you have the antenna cable. So if your antenna cable is very long, your loss will be high as well. And you need to check the type of the antenna cable as well. Okay. And because when you buy, so you, depending on the antenna type, you can ask the manufacturer or you can check the loss per meter. or per 10 meter, how much loss is there? Yeah, thank you.
Thank you very much, Dr. Manata. I will. We have multiple questions on the chat. I think two or three more, and we
Yeah,
have
yeah.
very limited time. But if you can keep the answer short, it will be very
Mhm.
nice. So, Dr. Dodo, could you ask your question?
Yeah, thank you so much for the wonderful presentation. It's really an interesting presentation. Now, my question is that the first question I would like to ask is, how effective is a low-cost GNSS receiver operation on dual frequency? In the course of your presentation, you did talk about the issue of there is that possibility of a low-cost receiver to have challenges while on a single frequency, because there has been a general belief that most of the low-cost receiver, GNSS receiver, operates on low frequency. And once they operate on low frequency, those of us from the geodesy angle, we find it difficult because we believe that for a single frequency, it is highly susceptible to the effect of the ionosphere. So how then do we handle that? Then the second question, you did mention on the issue of validation, which is very, very germane, very, very key. When we compute our TEC, how then do we validate our results? Given the fact that we have so many TEC computational softwares that are out there, which of the softwares can we use as a benchmark to be able to validate our TEC computation? Then my last question, number 3, is, can a low-cost GNSS receiver antenna, is it compatible with a geodetic GNSS receiver? Because of the area of position, those of us from the geodesy angle, we are very, very particular about positioning. Thank you.
Okay, so I will reply from the easiest one. The easiest one is the last question. For the
Yes.
geodetic receiver, whether you can use a low-cost antenna. So my simple answer is no, okay, don't use it. Because the geodetic means you are measuring at the millimeter level accuracy, maybe few millimeters or better than 1 centimeter. This is what you expect. And I have slide for that to explain with details, but I didn't prepare for this question because what you are measuring is very high accuracy, maybe better than 1 centimeter. That's 10 millimeter, for example. Okay, but the antenna you have is always bigger than 1 centimeter. Okay, it's maybe 10 centimeter or the big chopping. So how can you measure 1 centimeter with a 10 centimeter scale? Okay, so it's not possible. But to make it possible, the antenna, those high-end antenna, they have provided you the phase center value data, phase center data, and the phase center variation data. So when you do the geodetic receiver, when you do the processing for the position data, you have to provide PCO, phase center offset value, and the phase center variation data, because the center of the antenna is not the center of the electrical signal. Okay? So you need to know the offset value, and this must be used in the computation of the position data. So if you buy the low cost, the $100 receiver, you don't have those PCO and PCB data. They are not calibrated. You need a calibrated antenna, but those $100 receivers are not calibrated. So you have to go a little bit higher, maybe around $1,000. Or if you need even better, so the antenna gain very low noise amps inside LNA, and then yeah, all these calibrations, and then you need to protect from the like snow and all other things if it's a snowy area. to have a good observation. So this is related with your third question. Your first question was on the frequency, I think low frequency. So for the ionospheric, you do need a two frequency, L1, L2, or L1, L5, because with a single frequency, you can't estimate compute the TEC, but there is a model-based computation. I think that NECWIC also is valid for the single frequency as well. But in general, we do need a dual frequency receiver, L1, L2, or L1, L5. Okay. And your second question, sorry, I forgot what was your second question.
My second question is the validation of the software, the
Okay,
computation.
validation of software. Okay, I don't know how to validate. That's my problem. So actually, this is a question to the space weather experts, to all of you. I'm not expert on that, but when our people who help me, they process, so they also taking other software. They compare with the NECWIC model, they compare with their software, they compare with their other colleagues' software, and they were verifying each other themselves with the same data set. Okay, but we do need one like a master thing, and it may be the one provided by the receiver makers. Okay. But I don't see the TC and ROTI details, or maybe some of you, if you are using the Bernice software, maybe that will be the best, because Bernice is very widely accepted by geodetic community and many people around the world use for the very high accuracy data processing. Maybe we need some of those software as a
and that's the software I make use of, the Bernice software.
yes,
Thank you.
yes.
Yeah, thank you for those response, Dr. Matana. This is really good inspiring, interesting questions. And I will say that you mentioned a lot of things to be investigated as well. This, I think we could have like 5 to 10 masters thesis dissertation to work on with all of these things. So yeah, this is a really good. Is there any question besides those ones that are on the chat at home? Here, anyone want to ask one or two questions before I go to the last person on the chat?
Professor, thank you for the information. Is this presentation available to download anywhere?
This presentation?
Yeah.
No, I will share, yes.
Yeah.
Okay.
I will
Thank
get
you
it
so much.
from him, and I will make it available for the community, for the CONGA community.
Thank you.
Okay. So, any other question? I will let's Sestin ask his question. Is he still around? Sestin? Am I pronouncing his name well? I think his question is about let me see. Thank you very much for astonishing presentation, Professor. How these low-cost GNSS receiver respond to extreme storms? Oh, okay. Extreme storms. How would they respond to extreme storms? This low
Doc, I think you skipped my question.
Sorry?
I think you skipped my question. I should be the next, right?
Oh, yeah, I'm sorry. Do you want to respond to that quickly? And I will go to Dr. Emmanuel. Dr. Emmanuel, I'm sorry about that. My high skips. Yeah. Do you have any response to that question?
Oh, sorry, are you asking me?
Yes.
Sorry, what was the question?
The question is about if the GNSS, the low-cost GNSS receiver, can withstand, or how do they respond to extreme weather, space weather? Are they still accurate? Do they still measure up to the validation, particularly that figure that you showed? Do you still see that kind of well-behaved plots that follow the same path with the high-cost receiver? Is it still?
Yeah, of course, yes. So, sorry, what happened? You see, can you see my slide? Yes. So you see, these data are from two high-end receiver and the two low-cost receivers, and they overlay each other. Okay? And these data are for 3 days. So I don't see any problem using the low-cost receiver.
That's
But
good.
unfortunately, we don't have a data. We have a data, but this data is processed only for 3 days. So if somebody can help to process the data for maybe long duration, we can prepare the data for you.
Right. So I will come to you, Yenka, but before I go to Yenka, let's Dr. Emmanuel, do you want to ask your question?
Yes, thank you so much, Dr. Duna. Thank you so much. This presentation is very, very important, especially for the objective of CONGA, because low-cost receiver, we have been talking about it, and it seems to be the solution to help solve the ionospheric investigation within the African sector. So I just have a few questions. I just have one question, which is very, very important. Professor Udodotu has asked a very, very lovely question, which I'm also interested in. Then I also want to thank the professor for his presentation. Now, my main question is, how reliable are low-cost GNSS receivers signals strengths? Reading for consistent TEC and computation, given known resolution and data conversion issues. Because recent studies have indicated that the problem with low-cost GNS receivers is mostly has data conversion issues, then consistency in TEC computation. So how can we solve this problem if it's an issue when you were carrying out your research or your work?
I don't think so. I don't think so, because there's no such data compatibility issues and anything. But you have to set up the receiver, right? So you should know how to set up the receiver for the space weather monitoring. Okay, I did not explain how to set up the receivers and all. I think we did this. I think in my second presentation. I don't remember whether I explained or not, because if you are using the F9P receiver, for example, and when you purchase the receiver, when it's a brand new, and they have a default setting, and this default setting will not help you. Okay, so you should know how to set up the receiver.
Okay.
Like a mask angle, and also the some other threshold values, the output rate, whether it should be 1 hertz or whether it should be 10 hertz. So you have to set it once, and if you save it, so it will remain there. So low cost doesn't mean that it's low quality, okay? But you should know how to set up this, because the high-end receivers, they are already set up by the maker to provide you the high accuracy data. But the F9P or these things, they are sold as with a standard setup, because these devices are for the mass market, and you may be using it for automobile, you may be using for static observation. And if you make a different wrong setting, like for the static, there's a different setting, for the moving, there's a different setting. And if you want to log the data by car, you must have a completely different setting. Otherwise, you will have a bad data. Okay? So you should know how to set up the data. So that's the only thing.
Professor Manata, thank you for that response. And that leads me to say that we have a reason to bring you next year for another webinar.
Yeah, yeah.
It's
Okay.
very
We
exciting.
we invite you to
Mhm.
come and give us a webinar on basically on setting up these
Receiver
receivers
setups.
from
Yes.
the beginning to the
Mm.
end result. So that will be an interesting webinar for next year. So watch out for my email. I'm going to set you up for that next year. Thank you. And we have one last question from Yenka. Yenka, please go ahead.
Yes, thank you. Thank you, Olu. Thank you, Dinesh, for this very useful for
Thank
our
you.
community talk. And well, I have technical question, but I agree with Olu that we should have you again, maybe next year, for another technical talk. But just to release you so you can go to sleep.
Yes.
Since you mentioned that you have raw data that can be calibrated, we in the community we mentioned when we talk about TEC software, we call it calibration, and you touch a very weak point because since we don't have a reference, this is an iterated value, so
Yeah.
we cannot compare. So it's true. But I would like to know, maybe there is some volunteer or student or colleague that want to volunteer themselves to calibrate this data. Can you mention the period of raw data you have, and maybe the station again is only one station and the resolution? Because maybe with the students or colleagues are analyzing events, maybe this data can be useful for the study.
Yeah.
So
This data is actually from one station, but we had a sort of a campaign. I mean, in another team, we worked together. Okay, let's collect the data together in Europe, in Asia, in Tokyo, in India. I think we have a set of data collected at the same time, different locations. Okay, so I just need to collect the data. At that time,
yeah,
when we got this result, so everybody got excited because we also found many bugs in their software, other software, and I had many questions to them. And when they tried to reply, they found the bugs as well. And somebody said, "Oh, there was a bug in my software. I need to improve." And once everybody did, and then we had a very nice, good compare this type of output. So this is one way. So use the same data and process with a different software, and then compare the results. Because sometimes the researchers, they don't want to do this type of thing because he has been using it for a long time and it's okay for him or her. But suddenly when somebody comes, oh, no, my curves are a little bit different than yours for the same data. And they didn't have an opportunity to have the same data logged at the same time to check it. That's the problem.
Yeah, that's true. And we also recommend the colleagues to not mix the calibration methods, no?
Yes.
Because the result will be mixed as well.
So
okay,
my
so when
request to the space weather community is to use the sample data for like 1 week of data located in Tokyo, Asia, Europe, Africa, and use that data as a test data, and then use a different type of software and try to get the same result for the same data. And then you modify all the parameters in your software. So some software maybe it's fast to process, but some may be slow to process, but the results must be the same because it's the same data.
Sure. Taking into account, of course, that in our case for CONGA, low latitudes introduce complicated dynamics. So it's not the same like mid latitude. Okay, so when you can provide the periods and the stations that you have the raw data to calibrate, it will be very appreciated.
Okay, thank
you
you
very much.
Thank you very much, Yenka. Thank you, everybody. This has been a wonderful discussion and presentation. We want to thank you again, Dr. Manandhar. This is the second time we're having you on this platform, and the third time is already knocking on the door. But before then, I'm going to contact you. I have a group I'm working with Dr. Ivan Gaikin and Dr. Ryan. We are designing receiver, and we invite you to the group. This is a small group of CONGA as well, and this is the one we have now is the largest group. So, but before we come here, we meet together to discuss on progress. So in this kind of meeting setup, we want to invite you to see how we can actually come into the science space weather part of what you are doing to assist as well, and also to see how we can collaborate on other fronts with the hardware aspect. So I'll be reaching out to you in a couple of weeks or months to discuss that more. And without any other questions, will let us go. We have run over the time, way over the time. And think about, Dr. Manandhar is already close to 2 p.m., 2 a.m.
No, 1 a.m.
1 a.m.
No, it's okay. This is very
I
important for
apologize,
me.
honestly. This is really
No, it's
the
okay.
sacrifice for science, right? This is what we are talking about.
No.
Yeah. Thank you so much.
We have to manage because you're from Africa, Europe, different continents. So we have to manage.
Yeah, absolutely. Thank you again.
So next time I will make you midnight for you.
Yeah,
No, it's
that's
okay
good.
for me. Yeah. But
Anyway,
if possible, we can make maybe a 1 hour earlier. That will be better for me.
for next time, okay. We
Yeah,
will
just
try
1
that.
hour
Yeah.
earlier, not much.
We will try that because this meeting goes longer, and most of the time because of the information that is being passed, I don't want to stop. I just want it to keep going. So because a lot of people
And it's just once a month, so
exactly.
okay, no problem. I'm used to.
All right.
No, I have several meetings with Europe, and sometimes we have participants from US, Europe, and Japan, and that's the terrible one. So with respect to time.
Okay, absolutely. Thank you so much again, and thank you everyone for attending this 26th CONGA meeting. And I will see you next time on next month for another new edition of this discussion. Thank you.
Thank you.
Thank you. Thank you for receiving.
Thank you very much.
Thank you.
Thank you so much. Bye-bye.
Thank you.
Bye. Thank you.
Thank you, Inka.